hopefully it'll be okay. Now, if anybody finds any errors in my slides during the talk, go ahead and let me know during the talk. And then I will say, would you be willing to edit my slides for tomorrow's talk? Just as a warning. All right, so why should you pay attention to this talk? Do you guys know who this is? Who is this? Bruce Lee. Okay, so what's Bruce Lee known for? Wrong. Okay. Value types. Wrong. Okay. He's actually martial artist. Okay, and one of the greatest martial artists there was. And the reason is because he had a training in Kung Fu. And he did something which a lot of people really disliked at his time. And he said that Kung Fu is not as good as it could be in a street fight. Because Kung Fu gives you a whole bunch of rules, and he would prefer to be able to mix all these different martial arts, karate, whatever. And so his style, when he had this transition, when this epiphany came to him, is the style of no style. Which means, as we apply it here, the idea here is not to just say, oh, I'm going to program as a functional programmer. I'm just going to program functionally. No, the idea is we're going to learn the discipline of functional programming, well, as much as we can during this talk. And we're going to apply it to our problems that we have, but not exclusive to other ways of solving problems. Okay, so this is where I get in trouble with the Haskell camp, because they disagree with me there. They want to say just functional programming. This is where I get in trouble with the imperative programming camp. You know, we don't want any of this functional programming stuff, because this is really a hybrid. But I'm not going to talk about hybrid stuff today. I'm just going to talk about functional programming so we can understand this discipline. So we can use it as a style of no style. Now, as a brief, this slide has got too many words on it, but as a brief history of functional programming, how this came about, we have Alonzo Church over there, and he was a mathematician, and he was working on the fundamentals of math, and this was kind of popular at the time. So he's trying to break down math to its essential components, its tiny little pieces upon which you can construct everything else. And he came up with this idea called the lambda calculus. And for him, everything boils down to a function, right? Not even an integer. An integer is a function. Everything is a function. That was his idea. And that's from where we get functional programming from. But functional programming is not as much about functions as you might think. It just sort of came from, so he had this idea, an attempt at a foundation of mathematics, and he actually failed. So someone came and proved that his lambda calculus was not sufficient. There was some kind of problem with it. I forget what exactly it was. And he introduced types into his lambda calculus so that we had simply typed lambda calculus. And that sort of fixed some things, caused other problems. But anyway, that was what happened back there. So we have a lot of things, you know, lambdas, Alonzo Church, a lot of things named after him because he played with functions a lot. So next in line here we have Peter Landlin. Landon came up with this paper called The Next 700 Programming Languages. Now this was a really big deal because he loved math. And he basically had, for the first time, you know, put it in a very clear form, I would like to just program in math instead of just these machines. I wish I could program in math. And he made this language called If You See What I Mean. And he postulated that the next 700 languages could be based on this one language. Let's just use math as our language. And instead of having all these domain-specific languages, SQL, whatever, let's just embed it all in this math language. Let's make this language powerful enough that you can build these concepts on top of it. So what he did is he took Alonzo Church's lambda calculus and he put some sugar on it so you have enough stuff that you can actually do programs with. And that was the essence of his language. And if you actually look at this old paper, 1966, and you look at his language, it will look almost identical to like modern day Haskell. So this was a huge influential paper, and you know, if anybody's interested in reading it, it's not that hard to read, and it's a beautiful paper. Now next we have John Backus. Now does anybody know what John Backus did, what he's really well known for? What's that? Okay, a few things, but I heard Fortran was one of them. That was a big deal. So he's giving his Turing Award lecture, and some people say this was his apology for creating Fortran, because he came up with this idea of an algebra program. So he came up with his own programming language, very strongly math-based. There's it's not really used today, or anything like it is used today, but it's based on composition of functions. So again, we have this idea of taking mathematical concepts and building a language out of it. And although his language wasn't really his key contribution, his big contribution in terms of functional programming is that he popularized this research. He made it a thing. Before this, it wasn't a thing. So now beyond that, we have ML and we have Haskell and all this kind of stuff. But that's just sort of like a brief history. So we can see that it's very soundly based in mathematics. That's what functional programming is about. So here's my definition. Functional programming is math applied to programming. And principally in these three areas. So one is in languages. So let's make a language based on what we commonly know to be as math. Okay? That's one thing that functional programming does. But languages doesn't just mean you have to program in a functional language. Do you have to program in Haskell to be a functional programmer? Raise your hand if you think that's the case. Okay, we got one. So I'll, rather than ask the inverse question, I'll just assume that everybody disagrees. Because you can define, when you're writing your programs, you are defining a language for your users to write. Your interface is your language, which you're creating. So it isn't just limited. You can make your interface look like a language, a domain-specific embedded language, and it can be completely functional, and that's fine. So another place that it applies to is semantics. And we're going to talk a lot more about this later. So semantics, what does that mean? It means meaning. Semantics is the meaning of whatever your program happens to be. So like, I don't know how many of you were at John's talk, what he talked about, like int. You know, an int 3 has this meaning outside of the bits that it exists on your computer, right? It can be an actual thing, mostly mentally, or an entity, if you want to talk the elements of programming language. You know, functional programming is a lot about that, because we're trying to figure out the meaning of programs, and we're trying to create programs based on the meaning of concepts. And then finally, we get to style. There's a functional programming style, and it's basically using mathematics to develop your programs. So I would argue we don't need Haskell to do that. We don't need Haskell to do all of these things. And there's a lot of benefits, you know, because you can be Bruce Lee. All right. So this is my sale. If you guys don't get this sale, then you can go to sleep, check your Facebook account, whatever you want to do. Here's the effects of functional programming. The first one is simplification of complex domains. So if you come up with a mathematical representation of your project, what that means is you're getting rid of all the unnecessary details. Looking at it in its essence, getting rid of the non-essential details allows you to reason about it. Now, if we had huge, gigantic brains, we probably wouldn't need this. But because we're limited in our human capacity, it's very useful to get rid of these things which are like details, right? Or even having a concise syntax for things. You know, sometimes you look at these template codes and you're just like, oh my goodness, this thing is just gigantic in terms of all these type names and all that kind of stuff. If you can distill that into its essential form, it's a lot easier to think about it and reason about it. The second one is you can get strong insights into your programs from mathematical study. So you might pick up a math paper, you know, written in the 40s, and it will have, you can apply it to your programs, right? So a good example of this was the rediscovery of monads in the Haskell world. So, you know, before, I don't know when it was discovered, somewhere around the late 90s, before that time period, functional programmers didn't really have a good answer as to how to do I/O in a functional language, or what that means. And then someone discovered this in category theory. There's this concept called monads, and they were able to apply it. And so they were able to take the math and bridge it to programming. And that's the same kind of thing we're going to do here. We have inherent composability. Math is essentially composable. You know, you have function composition. When you distill things down to their individual pieces and you nail it right, then you can take these pieces and apply them together, sort of like how Alonzo Church was trying to come up with the fundamental pieces of mathematics as a whole. And of course, power from generalities. You know, when you talk about a group, or you talk about a vector space, these things are, they don't have particular types. a lot of types can fall into these mathematical concepts. So generic programming isn't just about a template parameter. Generic programming can be about a concept itself. All right. So let's get into it. Purity. This is an absolutely essential idea of functional programming, especially modern functional programming. So the definition of purity, so there's a bunch of them online. This is the one I grabbed. Free from what vitiates, weakens, or pollutes. And up here, we have a function declaration. It takes in an int and returns an int. So I want to ask you, what would it take for this function to feel, in your mind, as being pure? Okay, so people who already know the right answer to this, be quiet. All right, so I saw a hand up over here.
Well, yeah, but I already know the answer, so I can't say it.
All right. So, who has an idea? Just throw something out about how could this function be pure in some way? Sure. So, so the domain, which is like the incoming value coming in there, maybe it doesn't have an answer for value 6, right? Maybe it just asserts, so that would be a partial function, so that's a good one. And what about, go ahead. It does one thing. So what does that mean? The feeling, okay. It always returns the same output for the same input. Absolutely, yeah. Sure, so there's the argument that this is fundamentally impure because it takes in an int and it's not continuous. So the definition of purity that we're really looking for is first referential transparency, which means that if I give this thing a 5 and it returns a 6, if I pass it a 5 later on, it better return a 6. That's what referential transparency means. And then we also have no observable side effects. And this is a tough one to get. Yeah, go ahead.
Does it only have to return the same value for the same input if the input's in the domain of the function?
The question is, does it only have to return the same value for the same input if it's in the domain of the function? Okay, so the domain of this function is int. I would say that
This is a square. It doesn't have to return the same value. The input not. Value of the
okay.
are not underneath this.
Okay, so all right, let's say square root. All right, if you pass in -1, don't do that. That's undefined behavior. So that's just not even allowed. So we don't have to talk about it. All right, so that's what purity is. Now we also have this idea of pure values. Oh, and before we get to pure values, these directly map to mathematical functions. You will never have a mathematical function called plus, which shoots off a missile. Mathematical functions are always pure in this way. And it makes them easy to reason about, right? There's a benefit to it. That's why they call them pure. So we also have this idea of pure values. If I have an int, what can I do to make it pure? Very good. Yeah. Never change it. So if I have a constant int I equals 6, I is 6 at the beginning, I is 6 at the end, I is always 6. Just like the functions when they're pure, the same input always produces the same output. So when we're talking about purity and functional programming concept, we're talking about pure functions and pure values. Now if you limit yourself to only do this, some strange things happen. And go ahead, question? So the comment is that just because something is constant doesn't mean that it's not going to change.
I wanted to comment that I don't think a constant variable is the same as a value, because a value existed before life began. It will exist after life is gone. So a value is not temporal.
So the comment is that a constant isn't a value because it exists in time. So if I go like this and say constant I equals 6, when did this thing exist?
It exists in running program.
Well, I mean, it's here on the board.
It's the 6 that's the value, not the I.
Well, I would argue that it's a distinction without a difference, right? That we're talking conceptually at this point. Yeah.
Basically, I is just a different representation of the same value. Right?
That's right. So the comment is that I is just a different representation of the same value.
I think that because we're programmers, we create a confusion where maybe there shouldn't be. If I write I equals 6, I've got a variable I to which the number 6 has been assigned or placed in some storage. If I put a constant in front of it, well, it looks the same, but it's really not a different thing. That's actually fixed throughout my whole program, and the I doesn't, I don't even know that it refers to a memory location. It may just be a synonym for the value 6. So I think that our nomenclature that we use for C++ is sometimes confusing our brain on this issue.
So the comment is that sometimes the words that we use in C++ kind of confuses these things, and that's true.
That's probably why you're making this whole lecture.
Okay, so the comment is that I should rephrase it to pure variables or pure objects. No, I'm gonna use it like this. Okay, it doesn't vary, don't call it a variable. Sure. No.
I agree with what you said. I think the confusion is, or you could think about how mathematicians would, what mathematicians call variables. Like, you're writing a proof that says that x equals something. Later on, you don't say x is something else. That's always kind of happens.
Now, in Haskell, you would say that you are binding a name to a value.
Yes. So a comment is that in Haskell lingo, you'd say that you're binding a name to a value. Yeah. All right. So if you force yourself to only act pure in this way that we've just defined it, then let's take a look at what a pure list would look like. So here we have this list. Everything is private here. And we have these two constructors of the list. One creates an empty list. The other one creates a new list that consists of a front element and another list as the rest of it. Okay, so that's the only way that you can create a list with this class here. Now we have some accessors. One says, is this list empty? Another one which gets the front element of the list. And there's a precondition here, right? Because if it's empty and you ask what the front of the list is, that you don't do that, right? So this is a partial function, and a partial function means that not every input has a corresponding output. It's undefined for certain inputs, but it's still pure. Now, the rest is, the opposite of front. So if you have a list with at least one element, then front returns the front element, rest returns the list that comes after that. So there's nothing to say, let's modify the fifth element of this list. Right? There's really no modification in this at all. All we have the ability to construct lists, and we have the ability to ask things about it. And we can construct lists from other lists, but we don't have anything which really modifies the list. So that's the sense that you have with these pure structures here. And Bartosz is going to go more into that in his lecture. I'm not going to go into too much detail. So here we have a function on our list called map. Now let's go through what this thing does. So map takes in a function that goes from t to u. So it'll take in a t and it'll return a u. And remember, we're always talking about pure functions here. It takes in a list of t's, and what it returns is a list of u's. So conceptually, it'll use that function and apply it to every single element of the list. We check if it's empty. We return the empty list of type u. Otherwise, we call f on the front of the list, and we call map a recursive call on the rest of the list. So this is very typical in functional programming is you see this kind of recursion. But this is how you would develop something like a map. Question? Mm-hmm. So the comment is that in the STL we have transform. It's similar. Would I say that it's not functional? I would say that it's not functional style. Because it involves state. Okay, and the comment was there's also composition issues because of the dual iterators. Someone want to answer this for me? Okay, the comment is that you have to provide it for storage that it modifies as for a side effect. Okay, comment is the same thing as add to front. Okay. So comment is that you can make it return a range instead, and that would make it functional. All right. Yes.
That actually, to me, is very interesting because now we have the C++ letter in the middle and all that stuff. It's easy to imagine somebody saying, well, we should actually change the signature transform so it returns a whole new list. And then it would be actually a functional construct because there would not be any variables involved. And in fact, it sounds to me like it might even be efficient. And that would kind of be a little bit of a game changer as far as the way we've been using the STL algorithms.
Yep. So the comment is that now that we have move semantics and things like that, then we can make things a lot more functional, and it would be a game changer in terms of how we use the STL. So I'm going to avoid that issue. Now, does anybody see anything wrong with this function? Like why you wouldn't want to use this or any kind of issue? This is kind of a esoteric thing. Okay, one comment is not tell recursive.
This doesn't even matter in C++. There is no clear definition.
But anything else? Like what about,
Is there? It's not guaranteed though.
yep, there's the idea that you're creating a whole new list here, and maybe it uses more memory. Who cares about that stuff? But what I'm talking about is this first argument here, you can't convert a lambda into that sucker. You have to specify the types. So when you're working with these kind of functions like this, using a function object, you kind of got to do a little bit of hackery. So here we're taking in just any type f, and then you use type name to get the result of. Yeah, go ahead. Okay, there's a comment to wrap the stud function with identity. Okay, to disable the template argument instruction. Okay, so I don't know about that. Okay, so Eric is saying that wouldn't work. This works. There may be something more clever. This is what I'm aware of. But this is sort of a minor point. We do have to modify some things a little bit to get a decent C++ syntax that we want to use, or we want our users to use. So moving on. Functions aren't special. Int I equals 6, you can define I to be equal to 6. Here we're defining f to be equal to this lambda function here, just like you would a normal int. Here, g, we're calling foo of I, and we're assigning the result of g. So the idea is that foo returns a function. Over here we call bar with f. So f is a function argument. One of the key things is that in functional programming is that there's not this special distinction between values and functions. These are both valid values, especially when you're talking about pure functions. Is everybody okay with that so far? Okay. All right, so these functions that take a function as an argument or return a function, they're called higher order functions. It's just a name that they're called. So if you have at least one argument to your function, which is a function, or a return type which is a function, we call that a higher order function. And there's a lot of neat higher order functions, and we'll look at this one first. This is called fold. Now, some of you already know what fold is, some of you don't. I'm hoping that most of you don't, because what we're going to do is we're going to just, based on this signature, we're going to try to come up with an interesting implementation. So we see that we need to return a u. What we have available to us is a function which takes in a t and a u and returns a type u. We have just a plain old u value, and we got a list of t's. So what's one way that we could return a u in this fold function?
Return u.
Return u, yes, very good. We could just return u, but that wouldn't be very interesting, would it? We would just be ignoring the other arguments. So if we're not going to ignore the other arguments, then we're probably going to want to do something with that list, right? So let's break it up. It's either empty or it's not. So let's look at this first question mark. How many different ways can we return a u? Look. We know nothing about you. Yes. That's right. So, there's really not much we can do, right? In the is empty case, we got to return a u. All right? What about the other case? Well, we're not going to want to return u. Otherwise, it would be back to what we said before, and that's not really sufficient. So we're probably going to be calling this function f somehow. So let's do that. So what's the first argument to f got to be? I heard the front of the list. Yep. Now what's the second argument of f going to be? Okay, I heard u. Yep, so u is a possibility. Not very interesting, though. Or there's something more interesting.
You want to talk about the rest of the list, so presumably a recursive call the function on the tail of this fold function itself on the tail of it.
So the comment was that let's recurse. So that's right. So this kind of thing is common in functional programming. You get this type, and it almost forces an interesting implementation on you. But let's see what this fold thing does. Oh, well, first let's fix it, right? Instead of having the function, we have the type name f. Yeah. It's too bad we have to do that, but oh well. All right, so here's an image of what fold looks like. So we have this argument f, the function, and we have this base value u. Down here, these dots are our list elements. So we call f on u and the last element of the list. We call f on the result of that with the next element of the list, and so on and so forth until we get all the way up to the top and we get a result out. So does anybody have any idea as to why this might be useful or anything you can do with it? So there's accumulate function. I'm sorry? The comment is the same as std accumulate. It's not the same as std accumulate. Okay. So there's a comment that Well, that's just some Haskell lingo jingo. Let's, yeah. So, look at this. We can write sum out of fold here. Right? We just pass u is 0, and the function that we pass into it is just adding two integers together. So that's pretty useful. You can write sum with just passing these special arguments to fold. And here we have a list of int, but we really don't need this to apply to only ints, right? We could, give this template parameter, and now anything which supports plus and conversion from 0 can have this sum function. What about this? What does this thing do? So our first argument is add to front, and our second argument is empty. What does this thing do? All right, there's a comment that reverses the list. Nope. Copies it. Yep. This just copies the list. In a very esoteric way. But I'm sure we could write a more general version of this copy function, right? But the idea here is that this schema, with this special fold function, we can do a lot more interesting things with this. So here's how we can implement append using that schema. So we have add to front as the first argument, but instead of passing the empty list as the second argument, we pass another value. So now we get append operation out of this fold function. It's kind of neat, right? We can implement map using this fold function. So here we have a modified version of add to front that just quickly calls f on the first element of it. So this fold function, well, before I get to that, down here, this is just going to be gobbledygook to a lot of you. This is the mathematical representation of what we have above there. And I'm not going to explain exactly how this works, but the thing to take away from this is that we have a very concise, conceptual mathematical syntax that we can use as our mental model. And based on that, we can construct this blah. And that's what we want to get to. We want this nice, concise mental model. So, yes, question?
What would you ever need to copy one of these things? Once you created it, it exists forever.
So the question is, why would you ever need to copy it?
Yeah, I understand append gives you a new value. Why would you ever copy? One of the examples was, I just copied the list. Why would you ever do that?
Okay. So the comment was that, why would you ever use this to copy a list? You wouldn't. You wouldn't. This is just to give you an idea of a schema for making some of these more interesting things. Because this example here is just a slight modification of it, and so is append.
Well, you could actually, if you were using it as a very, very general algorithm, and in particular, this fold would be once called with the trivial function that copies the list. For other values of parameters, it would do something with the list, but for one particular value of the argument, it would just copy the list, like a special case, right?
Yeah, so there's a comment that it's a special case, and there it is. All right, so this fold function is kind of magic, and we'll look into why it's magic. I mean, we see that it has a lot of versatility. And I would argue that every data type has this magic function, and we'll learn how to figure what they are later on. So now we're going to switch gears, and we're going to talk about algebraic data types. So we want a nice mathematical representation of our types. And it turns out we can get everything we need with two types, one called 1, one called 0, and these two operations, sum and product. And these operations compose types into more complex types. So the first one is product. So if we have two types, A and B, the product of A and B is a type whose values have an A and a B. Does that make sense to everybody? Well, prove it to me. So how would you represent a product in C++? Okay, there's a comment, a struct with an A and a B in it. What else? I heard something else over here. A pair? Yep. So there's lots of different ways we can implement this in C++. Now, which one you choose is going to be dependent upon who's using your library. Semantically, they're the same. There's really no difference. Even performance-wise, I think these three are the same. But it may communicate something you want to communicate to a user. So John Lakos is the master of that. That's out of my realm of expertise. So what about this? Is this an implementation of A product B? Does this represent that?
I would think not, because you wouldn't, if you had two distinct ones, they could actually represent the same sort of thing. The unique pointer thing throws me off.
Okay, so the unique pointer throws you off. Well, I mean, that's intentional. So, what's that? There was a comment it could be null. That's right. So these could be null. Now, what if we said that, there's this invariant that these will never be null? Then does it represent AB like that? Okay, so there's the comment that what if these were both pointing to the same thing and one of them was modified and modified the other, so that wouldn't be good. There was a comment that they're not pure. So if this was constant, if it was a constant value, then you really couldn't modify what these things point to, right? So it really doesn't make a difference. So if you do have the invariant that these things can't be null, then yeah, I would say that these are a perfect representation of a product B. All right, let's look at the 0 type. So 0 is a type that has no values. So how would we implement a type that doesn't have any values?
An enum that just doesn't have anything in it.
So there's the comment of that you can create an enum without anything in it. So can you create an enum object as a default constructible? So, I heard void. Okay. Empty struct. So an empty struct, does it have a value? Yeah. Yeah. You can make it. It must have a value. So how can we get one without a value? How about this? Can you make one of those? No. It doesn't have a constructor. Okay, I heard the comment that you can still make one. How? Okay, there's a comment, turn your byte into that stuff. That's, of course, not allowed. Okay, so there's a comment that, listen, look, if you can't create this thing with a constructor, then you're doing something wrong, okay? Okay, I heard no, but this is my talk, so I say yes. All right. So what can we say about this pure function? Let's say this function is pure. It returns a 0, so what can we say about it? So I heard the comment, it never returns. So I heard the comment that it is 0, which is interesting. So here, what kind of implementation can we put in here? So how could you implement a function which is pure but has this type? Okay, no reinterpret cast. So, so I heard just call f of 0. So I did that, a little bit more sophisticated version. But they're both equivalent, right? They both have the same meaning. So if this thing has a meaning in functional programming lingo, then what the heck would we say is the return value of f? I heard the right answer. So we just call it bottom. Okay? So every type has this value called bottom. It just means that a function which is undefined for that value returns bottom for that value. So we have consistency. Now, in some languages, like Agda, you can get rid of this requirement that bottom is part of every type. But you lose something essential, like Turing completeness. So this is how we denote a bottom type. So I'm not going to go into more detail of this because there's a lot to this. There's very interesting things that have to do with this. But we're just going to keep on going, and just know that every type can have this bottom value. It's just necessary if you want to have sound mathematics. So now we have unit type. A unit type is a type with one value. So how would we implement that? I heard the struct without the delete. That's right. This type has one value, right? Just call it with the default constructor. There's no way that you can create a different type kind of unit, right? It only has exactly one value. So now we're going to go on to the final algebraic data type thing here. This is called sum or. So a sum b is a type whose values are either a value of type A or a value of type B. So how do we implement this? Speak up. Union. Okay. Very good. So we have union. But this isn't really enough information, right? Because I don't know if it's an A or a B. So how can we fix this? Throw in a bool. All right, so this is good enough. Now we have an implementation of A or B. Let me see. What about this? Is this a good representation of A or B? I heard a yes. Nope. So this acts more like bool product A, product B. Because you can still extract a B out of it even though has A is true or false, it doesn't really make a difference. Now, the comment is that this depends on your interface, and you're absolutely right. So is this a good representation of A or B? So I see some nodding, yes, right? We can set the A, we can set the B, but we have these nice post conditions here, which say that, does that say post? Ugh. Well, nobody gets credit for that because I'm the one who found it. So yeah, those are supposed to be preconditions. And oh, okay, so it is right. Okay, never mind. It's correct. What's that? Who was the one who corrected it? So would you be willing to help me edit my slides for tomorrow? All right. So this is how most people implement A or B. Something along these lines. Inheritance. You notice there isn't any inheritance in my fundamental data types, because it really just consists of an OR here. So I added a dummy virtual function in order to get proper inheritance or vtables working. That's just a tiny detail. But the idea is that if you have a pointer to an A or B, and we're assuming this is not a null pointer, it's just a pointer to something that exists, then we kind of do, well, we actually do have a representation of A or B. Now the idea here is there's lots of different ways that you can implement this. And we don't want our mind to get stuck in the details of how we can implement it. We want our mind to stay into this nice mathematical world because it makes it easier for us to reason about our programs. So does anybody have an even better way to implement this A or B thing? Boost variance. Exactly. Now this is better from a semantic perspective in that it closely matches what we're talking about with the A or B, but it may not be the right interface for the users that you want to provide. All right, so let's go back to our pure list. Now let's say we have an empty list. How many different kinds of empty lists are there of type A? One. So would any of these data types really work well there? So I heard the unit, and that's absolutely right. So for an empty list, we really just have a type with one thing in it. It's a unit. Now what about for a list that has something added to it? What type would map with that? What would fit? I heard something. I heard a product. So what would it be a product of? So these are our primitives up here. I heard A in a list of A. That's right. So it's a product of an A and a list of A. So if we put this together and we want to come up with the algebraic data type for a list, what would it be? So it's either going to be this or this. That should give a clue. One plus the second part. Right. Man, that is a very concise definition of a list, isn't it? That really captures it. So let's go back to the magic functions here. So here's how we would do the magic function of a unit. Let's say we're defining this type U to be equal to the unit type, so it only has one element in it. And we have our magic function. It'll convert a U into something else. Well, there's really nothing that you can do to convert it into something else. So there has to be exactly one value. So we just return T. So with our magic function, the first parameter is always going to be the type which we are computing the magic function of. The second parameter and so on are going to be the conversion functions to make it happen. So if we have our unit function here, it's just going to take in a single value that corresponds to the unit. Does that make sense? It might make more sense when I show some more of these. So let's look at the magic function for our product type here. So again, first type is a pair. Now if we have a pair of an A and a B, and we need to get some kind of T out of it, then you're going to need to pass in an extra function. These magic products always return some template type T. If we want to take consideration of all the possible values of pair, then it needs to take in an A and a B. Does that make sense? Raise your hand if it doesn't make sense. So then it must make sense to everybody. Oh.
I guess I don't follow what you're saying. What is this? Understand what the function does. Yeah, I don't get it.
Okay, that's fine. We're going to get to why you would care about these magic functions. So here's a magic sum. So again, we always return some type. We take in our value, this is our sum in this case, and these two things, these parameters, need to convert it into this somehow. Now, it wouldn't make sense for this to take in a function which like the product case, had an A and a B. Because with a sum type, you never get an A or a B, or an A and a B. You only get one or the other. So in this implementation, if it's an A, we return f of A of it. If it's a B, we return f of B of it. There's no other way to do this. Comment.
You look at the function as the magic function for the list that you wrote earlier. Why didn't you pass a special function for the case of the list?
Okay, so the comment was, in our list, our fold function, why didn't we pass in something where the list was, to handle for when the list was empty? And the answer to that is that we actually did, right? This u value handles the case when the list is empty. And then, because we have our product, we take in our function, or I mean our sum, we have our function, no. Because we have our product, we take in this function. So I'm not doing an exact mapping of how you would create a list, or a fold for a magic function for a list, right? I could sit out and I could write all the rules to create your magic function. But I'm just postulating here that a magic function exists for every algebraic data type. And what it will do, it will be sufficient to completely deconstruct it and reconstruct it with any kind of modifications you can want. And actually, it's the essence of this data type. So if you look at Church's original lambda calculus, this is how he would, he would say that this is equivalent to that function. All right, so let's move away from that. The functional approach. In one sense, the functional approach, you take this math and you use it to create an implementation out of it. So you can think in this algebraic data type space, and there's a lot more different kinds of math that you can use with this functional programming thing. You start out in your math, and from that you derive your implementation. That's one thing that you can do. It makes it easier to reason about, you get a good understanding, and so on. Another thing that you can do is you can take your implementation and you can try to figure out what are the fundamental mathematical things behind it. And what this allows you to do is it will cut out all of the inessentials, and it'll give you ideas for refactoring, like, oh crap, like this state doesn't really make any sense. The algebraic data type has this extra crap in there which doesn't need to be there. And it really makes this kind of ugliness stand out. So these are like two different ways that you can use this functional programming idea. All right, so moving ahead, let's talk about functions. Okay, so this A arrow B represents a type that takes in values of type A and returns values of type B. So this is just common notation for the types of functions. And the key thing here is that functions can be data structures too, right? If we extend our algebraic data type with now this function symbol, we can come up with data structures that use functions. And these can be very strange and interesting. So what is this?
The function returns an integer plus the sum. A pair including a pair with an integer and function sum.
So the question is, does it?
I read it in English.
So the question is this a constructor? No, this is just saying that, foo is this algebraic data type. Yeah, so an int we can count as primitive. So a recursive function definition of a function that returns an int. Well, this is just a type, right? And let's try to see if we can make this type in C++. How about this? Is this going to work? So I heard no. Yeah, it's not going to work because with C++ scoping rules, I can't really refer to foo on the left side of a type def, which is defining foo. All right. So okay, so there's a comment type aliases. I don't know if type aliases help here. I hear no. I hear yes. All right. Well, this isn't going to work. How about this? So we just have a structure. We know that we can refer to a structure inside of it. Has one member, which is this function. Does this one work? Is everybody okay with this one? All right. What's that? So the comment is that you can't calculate the size of the object. What do you mean by size? All right. So we can make this a little bit nicer by going like this. So here we're inheriting from standard function, and we're using perfect forwarding. So this object will actually act like a function. Does that make sense? Does everybody buy that? It's still a very, very strange thing. All right. Now, one other simplification we can make is that a function which takes in a unit is really just a function that takes in nothing, right? Because the unit can only have one type. So we'll just go ahead and remove that unit argument. And now we have a type in our C++ that implements this strange algebraic data type. But we still don't really know what it is. Let's see if we can make a value of this type. So do you guys agree that this is a value of that type? What's that? I'm missing a capture. Well, if foo is global, then I don't necessarily need a capture. Yeah. All right.
Self-preparation, I'm really not even sure that would work.
You know, it wouldn't work if that had captured something. So if we call foo and we get the first element of it, we get 1. If we call foo and get the second element, which is a function, right? That's the second part of it. And call first to that, we get 1. If we do the same thing, we get 1. So what does this thing represent? So the comment is that it's an infinite list of ones. So so I'm not going to repeat that. So the difference between this thing and a list is that a list can have an end, right? This type, can you make anything that has an end? Right, you said an infinite list. You said what this is. What about that? What about foo at the top? What kind of values does it capture? So it doesn't capture lists. It captures like only infinite lists, right? So we can call this a stream. And we can call that thing always 1. So we have an implementation of a stream. Shouldn't it say int stream on the right? Ah! All right. You're going to help me with my slides tomorrow. Thanks. All right. Right. So here's another int stream that we can construct. Same problem at the top. Thank you for signing up too. But now when we construct this thing, it's kind of strange, again. We create this function here, which takes in an int and returns a pair of an int and an int stream. And this returns that pair, and it uses standard bind onto itself with the next integer. And this one here just uses that, so we can create an int stream of our naturals. Yeah. All right, there's a comment that natural numbers start at 1 usually. Well, I'm glad it's only usually, not always, because then I'm correct, technically. So this is not that much code, right? I mean, this is not like a gigantic, barfing of template code right here. It's pretty simple. But isn't that strange, though? Don't you feel like this is a strange thing to do? Yes, right? And the question is, why is it strange? Because I would argue that if you're a functional programmer, this isn't that strange, right? Because you have access to this stuff. You think about things in this way. Some of the things that we do in imperative programming are very strange, right? Like dealing with pointers can be very strange for a lot of people. Certainly, the complex rules about, what function gets called when you give it a certain parameter is pretty strange. So this is completely natural for a functional programmer. And what I would really like, is for this not to be so strange for the average programmer. Because conceptually, it isn't that hard. Is it hard to learn? Sure, it'll take you a few days to get used to it. But after that, you open yourself up to a whole bunch of tools which you can use. So let's look at another strange thing. What is this thing? All right, so it's a function, right? What does it take in? Int. What does it return? A in a function of A. So you have this infinite choice of an int. You pick one, and you get some kind of value and another infinite choice based on int. This thing goes on and on to infinity. Now imagine a user interface where you present the user with a bunch of things, and they choose one of these things, and they get a whole new selection of things. So this is a fractal. Very simply put, and you wouldn't think to provide a user interface as a fractal, even if you're in an art type setting. But if you're functionally programming, this isn't that far off, right? And we could implement this in C++. You can follow some simple rules and get it implemented. So, all right, is functional programming only for doing strange things? No. All right, you can do a lot of strange things with them, and it's very fun. But there's also a lot of practical applications. So here's a practical app. Go ahead, comment. So the question is this how you would model nested menus? Yeah, absolutely. Especially nested menus that can be infinitely deep. Yeah. And believe it or not, I've used this to make an infinitely deep nested menu. So the comment is, isn't this basically the Windows event loop? I don't know what the Windows event loop is like, but it could be, this could be the semantics behind the Windows event loop. Yeah, sure.
Yeah, reactive programming.
Functional reactive programming. Yeah. So here's a more practical application. So there was a library in the week. The first BoostCon that I went to, they had this library in a week, and the idea was to create a new stream library. And this is, I don't remember if this is exactly the semantics that we came up with, but I think this is pretty close. So the idea was that you have a source which emits these values of type A. You have these transformers which can convert a source into a different kind of source. And then finally you have a sink which will take all this thing and do I/O operations. I'm not talking about this. This is just a magic placeholder for doing something. I don't want to go into more detail about this, except just to point out that when we did the semantics like this, it implied some fundamental functions that you would have. So here's one. You could take two sources and create a new source that just pairs their values together. If the first source expires, then the whole thing expires. Here we have two transformers. If you have a transformer, this transforms your source. Wait, before I get there, does everybody know what I'm talking about when I'm talking about sources and sinks? So imagine that a user is like typing in data. You know, that source can be like a source of characters. You can convert that source of characters into a source of ints. You know, you do some parsing, and now you have a source of ints. Then you want to actually do something with it. Maybe your sink just takes those ints and prints them out or saves them to a file or something like that. So this is what the source transformer sink thing is. This algebra directly came from the semantics. So if you have a transformer which converts from A to B and a transformer which converts from B to C, then you can make a new transformer which converts from A to C. And that just comes right from the semantics. Now, these two are pretty interesting because you can apply a transformer to a source directly and get a new source. So what used to be a source of a char is now a source of an int. And maybe those ints are interpreted in something, and I can convert that source from an int to a source to image, whatever you want. Or you can apply the transformer to a sink. So the thing which is consuming the data, maybe the thing that's consuming the data is just outputting characters to the console. So it expects characters. You can convert that sink using a transformer into something which consumes integers. Now, the thing to take away from this is not that this is some great design or anything like that, is that we got the fundamental operations directly from the semantics. We didn't try to do use cases or anything like that. We just tried to understand what the essence of the problem was, and then we were able to come up with this algebra. And this one actually was a surprise for me. I wouldn't have thought of that you can apply a transformer to a sink. And this is denotative design. This is an aspect of functional programming, which is you work on discovering the math, and then you derive your implementation based on the math. Now, thinking outside of the box. Before I really understood this aspect of development, so I had a math degree and a computer science degree, and it was an abstract math, and I never really connected the two, right? One was programming, one was math. Some math can be applied to programming. We're talking big O notation and all that kind of stuff. But when I understood functional programming, the idea of applying math directly to computer science, it opened up the doors for me. I wanted to go and grab every single math paper I could find to see if I could make some kind of use for it to enhance my programming. So what I want to urge people to do is to read some math and to try to apply these things in practice. Because I have a feeling that most of our data structures out there can be implemented, again, using functional concepts, and they'll be much more composable, much more easy to use if we just use the design technique. It doesn't have to be in Haskell. It can be in any language you want. As long as you start out with a strong math background, with knowing what you're talking about in the Platonic world of mathematical forms, you're going to be able to come up with solutions that are a lot easier and a lot simpler to reason about, and just libraries that are more fun to use. So, if you're interested, actually, let me do a digression real quick. So, this has nothing to do with functional programming. There was a previous talk where somebody talked about having a list and having an unsafe method to set link operators, because with a standard list, you have this sort function in it. And well, what if I want to make my own sort function? Let's go ahead and make some unsafe methods and just make sure that I restore everything to safety after I do that. Do you guys remember that talk? Yes. Okay. No. Don't do that. And you don't need to. So what if we do this instead? You extract fragments, which gives you this other data structure, which is more basic than a list, which is just a bunch of nodes floating around in a body. You suck it out. Then you can do your set link operations. You're not breaking any invariance here. And then you put it back in. And I talked to a very important person, and he approved this method as being a superior method. Did I? Sorry. I thought I grabbed it off of the thing, but my bad.
It's a different Sean.
Would the real Sean please stand up? All right. If you want to learn more about this, here are some pointers. The first is an old book called Denotational Semantics, and it basically showed how you can go from computer programs to just pure math, and it gives a mapping for that. There's a talk that I gave on the intellectual ascent to AGDA last year, and this is so we talked about algebraic data types. You can take the math to very, very extreme levels of abstraction, and that's what we do there. There's the Journal of Functional Programming. I read that thing all the time. Whenever I can grab my hands on it, that's what I'm reading, because you can learn about these new mathematical forms and how they apply. There was Modern Functional Programming in C++. That was in 2010. That is a mapping of algebraic data types and more other things into C++. It's kind of like a recipe book. And it goes all the way to type classes in Haskell and how to implement those in C++. There's also the Haskell community. Now, I'm a little bit hesitant to talk about the Haskell community because I've gotten so much pushback with these kinds of ideas in C++ in general from that community. But there's a wealth of information. If you learn Haskell, you're going to learn the math really quickly. Yes, go ahead. There's a recommendation of the blog, Lambda the Ultimate, and I agree that's a good one. And there's a book called Category Theory for Computing Science. This category theory is a very important set of mathematical constructs that can be applied to computer science, and this is a good book for it. And that is the end of my talk. Does anybody have any questions at this point? It's also obvious. I tried hard to make this not hard, but it's new concepts. Okay, so the question was, what about monads in C++? So I didn't cover monads, just like I didn't cover a whole lot of mathematical concepts. But practically speaking, we could really use a nice domain-specific embedded language for monads in C++. That would be awesome. You want to do that for us? Oh, you'd be the perfect person to do it, too. What about performance? I'm so glad you asked that question. So performance is when you come up with all your math and all this wonderful stuff. When you need to actually write the code that it corresponds to, that's when you become an engineer. And that's when performance actually matters. And you need to consider, yeah, I want this to match my mathematical model, but it might not look exactly like it because I care a lot about performance. I want to make it very performant. Yeah. So the question is, what about exceptions? If you're using the stream mechanism like we're talking about, then an exceptional event would be encoded like an optional value or something to that effect. Yeah, unless you can expand your semantics to be able to handle exceptions as well. And I don't know how to do that off the top of my head. So the comment is there's this thing called Rx, which implements monoids or monads. That implements monads in various languages. Cool. All right. Well, if there's no more questions, that's it.